Hello students. In this video we are going to learn about the polar form of the complex numbers. So let's consider a complex number z is equal to a plus ib, that is a plus iota b. Modulus of this number, like modulus of mod z, is equal to under root of a square plus b square, and argument is theta is equal to tan inverse of b upon a. We have already studied this in earlier lecture. Now let's call this modulus as also r. Now on the Argand plane we can plot this number z as, okay, on the x-axis we will take length a, which is the real part of the complex number, and on the y-axis we will take b, which is the complex part. So now we got this location of z. So this is the given number z. Now here the modulus of z is nothing but the length. So here I have written r, and the angle made by this z with the positive direction of x-axis is the argument theta. So here cos theta is equal to, obviously, adjacent side upon hypotenuse, which is equal to a upon r. That's why a is equal to r cos theta. Similarly, sin theta is equal to b upon r, and hence b is equal to r sin theta. Okay, so then z is equal to what? A plus ib. We can write these values a and b as r cos theta and r sin theta. We will write it. So z is equal to r cos theta plus I into r sin theta. If I take r common, then this number is cos theta plus I sin theta. Okay, so see, the same number z could be written in the form r into cos theta plus I sin theta, where r is the modulus and theta is the argument of that number. So this form itself is called the polar form of z. Okay, so this is polar form of z. Now, so we have this number z is equal to a plus ib, which could also be written as r is equal to cos theta plus I sin theta. Now we have Eilers theorem or Eilers identity, that cos theta plus I sin theta is equal to e to the power I theta. That's why z could also be written as r into e to the power I theta. Now this complex conjugate of z, which is denoted by z bar, is a minus ib, right, which is r into cos theta minus I sin theta, which could also be written as r into cos of minus theta plus I into sin of minus theta. Why? Because you must be knowing cos of minus theta is cos theta and sin of minus theta is minus sin theta, and that's why we can write like this. So now this is nothing but, see, here cos theta plus I sin theta could be written as e to the power I theta. Similarly, cos of minus theta plus I of sin minus theta could be written as e to the power minus I theta, and that's why this is the number. So for the number z is equal to r e to the power I theta, its complex conjugate z bar could be written as r into e to the power I theta. Okay, so let's try to understand this. Z is equal to a plus ib. Okay, we plot it here, a on the real axis and b on the imaginary axis. So this is number z. Now let's try to plot the complex conjugate of this number, which is equal to z bar, right? So this number z is equal to a plus ib can also be written as r e to the power I theta, where r is the modulus and theta is the argument. See, the z bar will be a minus ib. So the same length a on x-axis but minus b. Okay, same length b but on the negative of the y-axis. That's why z is here. So as you can observe, theta or the argument for this particular number, which is equal to z bar, is minus theta, right? And length is r only. So modulus of both these numbers, okay, so this number is equal to r e to the power I theta. As you can observe, for both of these numbers modulus are equal, but yes, argument are opposite. So number and its conjugate, here you can observe, for every number its conjugate can be considered as the reflection of that number about the x-axis. Okay, so for z and z bar, okay, every number and its complex conjugate, they are like image of each other and like in the x-axis. Okay, Now there is one question. Express minus 12 plus 4 root 3i in the polar form. We will try to solve this question. See, in earlier lectures only we have learned to find out the modulus and argument of a number. So whenever we want to write a number in the polar form, we are again going to do the same. Okay, first of all, see here z is equal to minus 12 plus 4 root 3i, which is equal to a plus ib. Here a is equal to minus 12 and b is equal to 4 root 3. So yes, r is equal to mod z is equal to under root of a square plus b square, which is equal to minus 12 square plus 4 root 3 whole square. If you go on solving, this will give you 8 root 3. Okay, so modulus of this number minus 12 plus 4 root 3i is 8 root 3. Now what is theta? So theta is equal to tan inverse of b upon a, right? So the values are tan inverse of 4 root 3 upon minus 12, that is equal to tan inverse of minus 1 by root 3. Now we know that tan of minus pi by 6 is equal to tan of 5 pi by 6 is equal to minus 1 by root 3. But in this particular case, a is negative and b is positive. That means we want the value in the second quadrant, and here 5 pi by 6 is the value in the second quadrant. So theta is equal to 5 pi by 6. Okay, so we got the modulus as 8 root 3 and argument as 5 pi by 6. So z could be written as 8 root 3 into cos of 5 pi by 6 plus I into sine of 5 pi by 6. So this is the number denoted in the polar form, which could also be written as 8 root 3 into e to the power I pi by 6. Okay, so here we have 8 root 3 and 5 pi by 6. Okay, so the number could be plotted on the argand plane again with the angle 4 pi by 6 and the length 8 root 3. Now let's try to understand the concept of multiplication using the argand plane and this Eilers form. Okay, number z1 is written is equal to r1 into e to the power I theta 1, z2 is equal to r2 e to the power I theta 2. Instead of writing it in the form of a plus ib, I have written in this form r e to the power I theta. But remember, you can always convert a number from one form to other form. Now here z1 into z2, the product of the two numbers, obviously will be r1 e to the power I theta 1 into r2 e to the power I theta 2, which is r1 into r2 into e to the power I theta 1 plus theta 2. Yes, if the indices gets added when we multiply the two numbers, right? So what does this tell us? See, when we multiply the two numbers, their moduli, they get multiplied and their arguments, they get added. So now in the diagram, consider this is the number z1, which is having the argument theta 1 and length r1, so modulus r1, and then another number theta 2 and another number with argument theta 2 and modulus r2. So the product of them will be having argument theta 1 plus theta 2. So what you have to do, you have to draw a line with the angle of theta 1 plus theta 2, and its length should be r1 times r2 or r2 times r1. So this is how we can interpret the multiplication of the two numbers on the diagram. So whenever you are multiplying the two numbers, you should try to remember this particular thing. It will help you to solve many problems in the competitive exams quickly. So let's try to solve this example. Z1 is equal to minus root 3 plus 3i. So this number could be written in the polar form as 2 root 3 e to the power I 2 pi by 3. I think you can solve this problem yourself and check whether this is correct or not. Then Z2, let's take Z2 is equal to root 3 plus I. So this number in the polar form could be written as 2 into e to the power I pi by 6. So what will be the multiplication? So Z is equal to Z1 into Z2, which is equal to 4 root 3 e to the power I 2 pi by 3 plus pi by 6. So what happened? The moduli are multiplied and the argument, it is added. Okay, so we get the answer 4 root 3 into e to the power I pi by 6. So this is the answer. Now can we convert this number into again form of a plus ib? So okay, we can write this number as 4 root 3 cos of 5 pi by 6 plus I sin 5 pi by 6, which is equal to 4 root 3 into minus root 3 by 2 plus 1 half I, because cos 5 pi by 6 is equal to minus root 3 by 2 and sin 5 pi by 6 is equal to half. So we multiply this and we get the number as minus 6 plus 2 root 3 I. Now by direct multiplication we can also solve this problem. So z1 into z2 will be equal to, we write both the brackets, minus root 3 plus 3i into root 3 plus I if we go on multiplying, again we are going to get the same answer, but okay, this is the method we have already used. So by the earlier method also we get the same answer. But okay, you would say that this method, the earlier method itself, is a faster method. Yes, it is, but at the same time you must understand the other way of multiplying the two numbers. That would be helpful for many of the problems. So now in this particular case, what happened is the first number, okay, Z2, the second number is having the modulus 2 and angle 30 degrees, pi by 6. So we have this number Z2, right? This number Z2, which is having the modulus 2, length 2 and the angle 30 degrees. Then we have the other number Z1. So Z1 is having angle 120 degrees, which is 2 pi by 3 radians, which is 120 degrees. And its length, okay, its length, it is 2 root 3. Okay, if we multiply these two numbers, our resultant number will be at 150 degrees. Try to understand this, 150 degrees, which is 120 plus 30. So what we have done, to this 120 degrees, we have added again additional 30 degrees, and the answer is on this line, making the angle of 150 degrees. And what is the length? Okay, here the length was 2, here the length was 2 root 3. So here the length is product of the 2, that is 4 root 3. So in this way, we can interpret the multiplication and use it for other problems. Now, what will be division? For a division, if we have two numbers, R1 is equal to, Z1 is equal to R1 e to the power I theta 1 and Z2 is equal to R2 e to the power I theta 2. So Z1 upon Z2 will be obviously R1 upon R2 into e to the power I theta 1 minus theta 2. What does this tell us? If we have Z1 with length R1 and angle theta 1 and another number Z2 with R2 and theta 2, okay, so the resultant will be at the angle theta 1 minus theta 2. So what I am going to do is, first of all, we have Z1 over here at the angle of theta 1, okay, we are subtracting, we are turning it, so subtracting the angle theta 2 from it, and we reach here, and okay, this is the position at which we are going to get the answer. Okay, this is the angle, this is the argument of the resultant, and what will be the modulus of the resultant? Okay, modulus of the resultant will be equal to R1 upon R2. We have to take the ratio of the two arguments. So remember sign convention in these cases. Whenever we have positive angle, it is to be measured anti-clockwise, and when we have negative angle, it is to be measured clockwise. And that's why whenever we have minus of 30 degrees, so if we want to subtract the angle or add the angle, you can decide it according to the sign conventions you have already learned in the chapter trigonometry and measurement of angles. Now here some interesting facts are there. Let's say we have number I. So number I, which is 0 plus I, could be also written as e to the power I pi by 2. Modulus is 1 and e to the power I pi by 2. So what does this mean? If we multiply any number by I, okay, so what's going to happen? Its modulus is not going to change because the modulus of the new number I is 1, okay, but its angle is going to be changed by exactly 90 degrees, pi by 2. Okay, so when we are multiplying a number by I, we are rotating it anti-clockwise by 90 degrees. So Z into I is equal to R e to the power I theta into 1 into e to the power I pi by 2. So the resultant is R into e to the power I theta plus pi by 2. So we have a new number which is having the same modulus, but the angle is changed by 90 degrees in the anti-clockwise direction. Similarly, if we multiply by minus I, it will be the rotation by 90 degrees in a clockwise direction. At the same time, you should understand that multiplying by I is equivalent to multiplying by I is equivalent to dividing by minus I. Okay, so both of these things are going to give you the same result. Now there are many iterations or many variations of this particular thing. You can do it yourself and use them to solve your problems. Okay, so thanks for watching.